Here's another problem that I'm going to write a solution for. Honestly, a lot of these problems at first are just going to be kind of random problems, but if you're watching this, you're probably taking some type of algebra class or studying something with algebra. So if you have any suggestions or any fun problems that I can provide solutions for, or try to at least, go ahead and leave any suggestions. I don't really have, I don't really have any plans. I'm self-studying as well. So I figured I might as well make some videos that somebody else can watch and maybe get something out of, so it doesn't hurt. But this problem says, suppose that G is a non-abelian group of order PQ, where P and Q are primes. Prove that G has a trivial center. So let's go ahead and get started on this. So proof. So let G be a non-abelian group. So let G be a non-abelian group which has order PQ. So this has order PQ. And we want to prove, so P and Q are primes. We want to prove that G has a trivial center. So let's recall that the center of G is a subgroup of G. So recall the center of G is a subgroup of G. And since it is a subgroup of G, the order of the center has to divide the order of G. And in this case, if the order of G is PQ, then the only possibilities for the order of the center are PQ, P, Q, and 1. So thus, let's write this out. So thus, the order of the center is either PQ, so the product PQ, or just P, or just Q, or just 1. And right away we can eliminate PQ, because if the order of the center is PQ, it has the same order, then the center is equal to the group itself, contradicts the non-abelian part. So right away the center cannot have order PQ. And that's more or less how this problem is going to go. We're going to eliminate the possibility of P, the possibility of Q, and we're just going to be left with a trivial center. So that's the way that this problem is going to go. But before we continue on with the other two cases, I want to state an exercise I solved in a different video. We'll call it a theorem here, and this is going to help us prove the other two cases. So the theorem, or the exercise, said if G mod its center is cyclic, then G is abelian. So you can go ahead and prove this yourself if you like. You know how in the textbooks they say the proof is left as an exercise to the reader. Well, here the proof is left as an exercise to the viewer. So you can go ahead and prove this yourself, or you can just go watch the other video. It's up to you. But we're going to use this this theorem here to prove the other two cases. So let's look at the case where the center has order P. So if the center has order P, then if we look at the quotient group G mod its center, then the order of that group, of that quotient group, so the order of this quotient group is going to be Q. Because G has order PQ, if the center has order P, PQ divided by P, that's just Q. But Q is a prime, so that tells us that this quotient group here must be cyclic. Remember, groups of order, of prime order, are cyclic. So thus, this group here is cyclic. But this theorem here that we proved in a different video says that if this quotient group is cyclic, then G is abelian. That contradicts our assumption here that G is non-abelian. All right, so that eliminates this possibility. It can't have order P, otherwise this quotient group is cyclic, and it shows that G is abelian, which of course G is not abelian. And for the order Q, it's the same exact, it's literally the same argument. So if the center has order Q, then the same way this quotient group here is going to have order P. And of course, P is prime, so then this quotient group turns out to be cyclic. Again, proving that G is abelian, giving us the same contradiction. Right, and then so if we reference this theorem here in both cases, if it's cyclic, then G is abelian. So both of these give us contradictions. So that eliminates the possibility of Q, and it leaves us with a trivial center. So then thus, the order of the center equals 1. Shows that it's trivial. That completes the proof.